Hello everyone, August 26th. It's a bit late today. And I was, sometimes when you start working in the morning, I was like, okay, I'm only gonna work for like maybe an hour and then do something else, like let's do LeetCode. But then 1 hour leads to another hour, and then we find a bug, and then leads to another hour, yet another, and then once you start realizing it, it's already in the evening, right? It's time flies very fast. But fortunately, I mean, the problem I was solving was with the app. We had some requirements to make some components dynamic, and we solved it. But then, when you think about you solving one problem, there are others popping up. I mean, mostly because I mean, we didn't have time to write unit tests for this. So right now, it's everything has to live in my head. Like if something breaks, and I have to really think about it. Okay, why does it break? I would love to settle down and write some unit test, but we can't. I mean, we don't have time for that. All right, anyway, let's go for it. Enough of my rant. All right, verify preorder serialization of a binary tree. One way to serialize a tree is to use preorder traversal. When we encounter a non-null node, we record the node's value. If it is a null node, we record using this, right? So what the hell is preorder? I think it's in this root left right, right? Root left right, root left right, root papa, right here, right papa, coming back to pa 6 papa. Okay. Given a string of comma separated values, preorder return true if it is a correct preorder traversal serialization of a binary tree. It is guaranteed that each comma separated value in the string must be either an integer or a character pound. I think that's, I call it pa, representing null pointer. You may assume that the input format is always valid. For example, it will never be something like this. You're not allowed to reconstruct the tree. You are not allowed to reconstruct the tree. Integers in the range, and this separated by. Alright, so we have this, then we want to know if it's a valid, right? So basically, if we can build a tree out of it. But you are not allowed to reconstruct the tree, so we cannot reconstruct the tree. Which means if we reconstruct the tree, we will find out that it's not good. How do we do it if we do reconstruct the tree? I mean, that if you're not allowed to do it, that means it's harder. So we always try the easier solution just to see how it works. So how it works, we have, this is the root, right? And then the next one will be the left, right? So I say the first one is going to be the root, and then the left will be equal to this, and it has, and then we're going to go its left, right? It has, and then go its left, and that will return a null, okay? And null will go back here, we'll go its left, its right, right? As a null, and then go here, and then go to the next one. So basically what we're doing is at each point, we're just going to pop it out, right? We just pop it, because when we want to go into the list, I mean, we can also increment the index, right? Increment the index. Like after we're done with one, we increment the index, and then 3 will go here, and then blah blah, and then go 1, 2. So this one will return will be go back here, and this one will go to the right. Okay. So what will happen in this case? Well, in this case, I say 1, and I will go left, and then boom, it ends, right? It ends. But Yeah, but we are at a node. We're trying to see if this node is going to be, so we are at a node, but there's nothing more left. So we say, oh, that's not good. Okay, that's possible. And in this case, 9, and then that's it. And then we have something left. So that's a false. Yeah, I mean, they say do not reconstruct, but let's try it. I mean, it doesn't hurt to try it. I mean, I was thinking like in the actual interview, we can go through this process. We just, we go through, say, this is how I would do if we need to reconstruct the tree. But this is just, for me to go through so I kind of have an idea of how this will work. And after we done that, then it's time when we say, okay, now we're going to do is try to do it without reconstruct the tree. So we can have to use a tree node, right? Val, no. How do we do this? Self def initiate self val. Yeah, and then I think self.val equals val, and val should be an integer. And self.left is going to be none. Self.right is going to be none. That's the node. Right? Then we try to solve this problem. Basically, I think it will fail, right? It will fail if the tree cannot be constructed. If any value is followed by 2, hold on. Let's try it first. So we're gonna first construct the tree, right? So def construct. It says do not construct, but we will construct self.index. We start with 0, right? Construct. And construct. We don't have to pass in anything. We'll return a tree node. No, we'll return an option tree node. Optional, right? Because it could be a tree node or it could be none. Okay, so what do we do here? This one will return. I think construct, we call construct again. Right, and then we fail, right? Because we do this, and then we call construct on self.left equals construct, and then we'll call construct and already increment. Now we consume this value, we increment, and we do here. It's done. When it's done, it's a none. Then we just return, right? And then we try to do right, and do right. We see nothing, right? We see nothing. And then we just return none, and we have to have another, I say self.valid. Valid, let's say it's going to be true, right? So anytime it's invalid, then we will note. Okay, so construct. So if self.index equals len preorder. Oh, we have to, so preorder list equals preorder.split, and split based on this. So list, right? If it's equal, which we shouldn't be, that means we are entering a node, but we don't have the preorder for it. Then we just simply say self.valid equals false, right? And then return none. Doesn't matter, right? So it's equal. If it's not equal to smaller, that's fine. And then what we do is get a current value, right? We get the current value. So we have a current node, what equals tree node, preorder list self.index, right? After we do that, self.index, we consumed it, so that one increment. And then we can say node.left equals construct, right, again. And then node.right equals construct. So left, construct. After finish, right, construct. And after we finish, we return node, right? So we can just say, we don't even need, we just construct, we call it, right? And we say, when the return self.valid, but there's another case, right? Which is, hold on, so if this, in this case, right, after we consume the last one, the tree node, it doesn't really matter. We don't need to have a value. We don't need to have a value. It doesn't matter. I just put the values in. That's fine. Because we don't need a tree. So we'll do this, right? Actually, no. We say if val, right? Val equals this, right? We say if val equals this, return none. Else, say int val, and then we have to increment no matter what, right? We increment, and if it's this, we return none. It means we don't keep going that way, and then if not, we do blah blah blah, and then we return this. So in this case, after the last one, self.index will increment, right? Increment. And an increment, so when it came out, it will be, when it check for valid, and if valid is true, we'll also check for and self.index shall equal to len preorder list. That means we have traversed the entire thing. Not like this. This one we will end right here, so we don't keep going, and then the index will be here, right? So we'll return these two. All right, just give this a shot. See how we go. Run a code. Let's see. str object has no. Split. I did a spit. All right, it's split. All right, let's try the test case that's wrong, which is 1 and the star, right? 1 and the star. False, that's good. I think the other one is like this, right? Yeah, that should be false. And the edge case, this should be false, right? Yeah, this is false. Yeah. But this shall be true, because that's just an empty tree. Oh, we did get to true. Alrighty, let's try this. Pending. Accepted. So this one works. Right, so this one works. because we reconstructed the tree. However, it is not following the requirement, so we won't count this. What's the runtime? On, because each one visited once. On runtime, on time, and on space, because we have to create n nodes. That's the runtime. Execution time. I shouldn't say runtime. Execution time. Oh, very slow. It barely passed 64 milliseconds, or a 5% ranking. All right, so now let's get real. How are we going to do this without reconstructing? I mean, if we don't reconstruct, maybe we can use... I mean, it would be the exact same thing. It's just not using reconstruction, right? We can do exact same thing. What you can call it. Yeah, I think it will be the same. It will be exactly the same way, right? It will be exactly the same way, but without having to run a node. Index, we do this. Construct, we do construct, but we're not constructing the tree. There's no tree, right? There's no tree. So we're going to say this. That's good. Now we don't have to return. We can just directly return a Boolean value, right? So we just say this one will return false, right? And then it's current value, blah. If this, I will return true. Then we don't have to do this. We simply call construct twice, right? Call construct twice. So the first time we call construct, we're going to say if construct. If it's false, then return false. If it's true, then we will say if construct, if not. We'll say if not construct, or, no, that would be short. Okay, if not construct, if one side is already false, then we don't have to go to the other side. So we say or not construct, right? So basically we call construct twice, because each time we update the value. So we say if not construct, which is called the first time, if I return false, then we don't evaluate the second one, we just return false immediately. If the first one is true, then we do the second one. If the second one is false, we return false. Only if both are true, then we return true, right? And then we return construct. But this construct has no nodes involved. In fact, right? In fact, I think it'll be. I like to pop, right? I mean, it's fine. It's really fine. You don't have to pop. You can just do this, right? You do this, and then we can reverse it, and then every time we access the end, and after access it, we pop it. Pop it. Maybe. Let's be fancy. And then we don't need any of this, right? We just need a reverse list, right? Reverse list will be preorder, and then can we call it .reverse? Oh, we probably can call it reverse. Okay, I don't know. Let's try. 1, 2, 3, 4. Reverse a reversed object. Okay. How about a.reverse? No, a cannot .reverse. So we have to list it, I guess. Reversed object. Yep. All right, let's call list reversed. Actually, I don't know. It's called reversed A. B is this. Okay, can we call B0? Is not subscriptable. I don't know. But we can call for F in B, in F. Yep, it, and then B. Is it iterator, right? I think it's, yep, it's an iterator. Reversed return iterator. Can we take advantage of it? Yeah, we can take advantage of it. We'll just call next. Let's try this. Turn that into iterator, right? And then, how do we know? Ooh, B dot next B stop iteration. Check. Wait, can we check? Stop iteration. I don't know. Can we check for that? It gets next unit, but you do not check everyone unit. You have to try. Huh. Do I like that? How big is the list? 10 to the 4th. 10 to the 4th is not that huge. It's not that huge. No, I don't like it. No, I don't like it. I mean, it reduces memory usage, but I have to try. Like every time I have to try it. No, I like just turn this into a list. Let's just go straight, right? So, if not, right? If not, reverse list, return false, right? So pop everything, return false. Now val will equal to reverse list dot pop, right? And then if val equals this, return true. And if not, this, okay. Return this, okay, solution 2. Now this one, we can actually run our own test cases because it's not based on creating a tree. Oh, actually, we can do the other one as well. I just realized because it's not based on a tree. We create a tree ourselves, so that's why we can do it. All right, 1 pound, and there's a false. It's the next one. 9 pound 1. That is a false. And pound itself is a true. Okay. Preorder is valid preorder. Okay. If not, I forgot to put this on it. Pass, but fail the first one. Huh. Interesting. How do we fail the first one? So value, and then we'll construct, if anyone is false, let's print value. Let's see. Why is the first one fail? Because we forgot. Oh, shoot. I forgot to take away the comma. Yeah, the reverse. I think it take the. Ah man, come on. All right, we have the split. We have to split by this, right, and then reverse it. Oh, oh, oh yeah, this is right, but we still return false. Okay. Oh. Oh, darn it. I cannot have. Yeah, you don't have to. This is a string. Jeez. There we go. Now we're good. All right, again. Let's check all the others. 0, 1, 2. Return construct and not rev list. There we go. All right, so this one is we did not construct a tree, but we almost construct a tree. All right, so we almost construct a tree. So let's try this one. Pending, judging, passed. How fast is this one? This is exactly the same, but without constructing the tree. So this one is the same logic as solution 1, but without constructing the tree explicitly. So on time on space, because we did this, but much faster. 36 milliseconds. We don't have to do this part. Then we got a 54% ranking. All right, if we're here, then the next one will be just try to write a recursion in using stack, right? Using stack, like 3. So we're gonna push 9 to the stack, right? And then we go left, so push 3 to the stack, and go left, push 4 to the stack, and then come in this. This is the left, which is good, so we don't push. And then coming, this one will be the right node, right? And we don't push. And then once we have this, we shall pop this. How do we know that it's on a So this one would be left, right? And then basically it's like how do you do traversal using stack? Right? We'll push one of this in. Yeah, we push it in, right? We push it in, and then we encounter another one, and what? Then if we see okay, 3 will be this, right? And then it will be 1. And then we go papa, done. And then it will be, so how do I know 3 is done? Well, we don't know, right? Do we know 3 is done? We check the next one, right? The next one is good, so we push the next one into the stack. And then we check the next one. And if the next one is this, right, then we say we don't push into the stack. Then we switch. Now we're going to go to the right. And then this one is this. Like whatever we push in the stack. But now it's this. Then I say, okay, if the right node is this, then we are done. So we pop 4, and now we're pushing 1, right? So we pop 4, and then we switch back to, so we're still on the right. So 4 is the left, so it pops, so we're pushing this 1 is on the right. Papa, so done, 1 gets popped. So then I'm pushing 2. 2 is on the, I mean, it's possible, but I'd like to use Recursion to do this. Anyway, alright, let's take a look. I think I am going to, if there are people using the stack, then I'll try to figure out how that one works. Anyway, so this one is LeetCode 331, right? 331. Good problem. Easy solution. Preorder traversal. Ooh, look at this. O1 space. Oh no, it's not O1 space because you have your split. Alright, so what is the magic? Why people downvote? That is... Like, don't downvote. People write this up. If you have anything to add, just leave a comment. Alright. Okay, we define binary tree by saying two things. Each null node has 0 children, and each non-null node has 2 children. That's true. We say that a tree is valid if it follows both of the above conditions. Basically, looks like we need to keep a track of the number of children. Slots can fill in children. So one gives 0 children and consumes 1 space. Gives a total of -1. A null node gives 0 children and consume. So we count the number of children. Wait, hold on. What are we doing? Keep track of the number of children. A null node consumes 1 space, but produces space for 2 more. So -1 for a non node and +1 for valid node. We only need to count the slots. Slots themselves follow 2 more conditions. They're always larger than 0 during the program run. They're at the end of the run. Slots. What are slots? Call it slots is the number of, keep track of the number of children. So let's say we start from here, right? So it's a non-null node. So it has 2 children, right? And then we go here, that's non-null. So it has 2 children as well. Okay, so this non-null, so it provides space for 2, right? And now it has space 2. And then this one has space 2. So that's 4. And this one has space 2. That's 6. And this one does not provide space. So it's 0 space. Offers 0 space. But it consumes. This offers 2 space, right? So each comes in. This comes in. When we start, we have 0 slots. So this comes in. it takes one slot, so it's -1, but it offers 2, so it takes 1, it offers 2, so in total slots, it is +1, right? So gain 1 slot. Hold on. A valid node, right? Let's consider this one gives 2 slots, and then this one will take a slot, right? Will take a slot and offer 2 more. So each valid node will generate 1 slot, right? Each valid node will generate 1 slot, and each null node takes a slot. It doesn't generate, so it's a -1. So as we go through, so just plus, 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 minus, 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 minus. So you're telling me that at the end, the number of slots, yes, the number of slots should be 0, because if it's correct, if it's valid, right? If it's valid, that means all the slots shall be filled, right? All the slots shall be filled. So in total, the slots should be any extra slot, right? Any extra slot. And we start with 1 extra slot because we always have one thing at the start, right? We have 1 extra slot. So we just start with 1 extra slot and then we run it. And so basically we just count the number of none node and then count the number of this. And then they shall be, the number of none nodes shall be 1 larger than the number of nodes, right? Is that the case? If we're talking about the slot idea, right? So each one will have, so we give a free slot, right? We give a free slot, and then we count the number of actual nodes, right? And we'll have a number of actual nodes. And we say for a valid node, it provides, it offers two slots, and it takes away 1 slot. So in total, it's +1. And then the none nodes, right? The none nodes, it takes away 1 and offers 0, so it takes away 1. So in total, we're talking about when we finish this, if it works, then the total slots shall be 0, because every slot is occupied. Yes, every slot is the number of space that has not been occupied, right? So we provide, so the valid node saying that we will always create 1 more slot, and then the none node will always decrease a slot. So in total, yes. So if this is the case, then it is a very simple problem. It's just string operation. So if we're talking about a string operation, all we need to do is to count, right? So what do? We remove, we can count a pound, count this. So we can say preorder dot count. I think we have count, right? Oh, it does not. But if we do split this, then we can count. So we can say preorder list equals this, and preorder list dot count. And count this, right? Count this shall equal to the other one +1. Right, so remaining should be this one plus 1. So we can say count null equals this, right? And then we'll just return count null. I'll just say count null equal to count null plus 1 equal to len preorder list minus count null, right? And that's the idea. Version 3, fail. I see 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Oh, that's minus 1. My bad. My bad. There you go. And we can even simplify it. We can call it 2 times, right? 2 times this equals preorder list. Because this plus this minus 1, yeah? And we can further simplify by not doing this one here, by doing this one here, right? So now it becomes 2 lines. Well, so this, I think is correct, so I'm gonna courtesy. Very, very smart idea from using a concept, using a slot concept. Each non-null node takes 1 slot and offers 2 additional slots. So the net slot for non-null node is 1. Each null node takes 1 slot and offers 0 slot. So not next, the net. So the net slot for null node is minus 1. For preorder to be valid, there should be no extra slot left, right? There should be the net slot of the net slot should be 0. For to be valid, the net slot after going through all nodes should be 0. Therefore, we just need to count. Therefore, we just need to count. The number of null nodes and right, do the comparison of the two. The number of null nodes will always be 1 larger than the number of non-null nodes. Yep, that's it. Yeah, initially slots is 1 here. I can actually offer an explanation. Because initially we have net slot 1. Net slot equal to 1. to hold the root. And then it's just, wow, it's very, very good. Very smart. Brilliant. All right, let's try this. Submit. Oh, we got a wrong answer. Huh? Hold on, what the hell? 2 times don't count, that's 3. Oh, wait a second. Wait a second. Oh, wait. We cannot. Oh, wow. Huh. I thought we just need to count. We have to go through. We have to go through. We have to traverse it and then make sure that the slot does not go to negative. I see the point. Oh, okay. This is not right. So for the proof to be valid, as we iterate through each node, the net slot must not be negative, and at the end, the net slot must be 0. Yeah, we have to do this now. I thought we can be cheeky and smart, but no, we cannot be that. We have to go one by one. So and a good set is 4, right? 4 val in pre-order list, right? And then the slot, initial slot is 1. Right, initial slot is 1 because we need to hold the root, right? So if val is equal to this, then slot minus equal to 1. Else slot plus equal to 1. Let's write in one line. Slot plus equal to minus 1, right? If this, else 1. And then after that, we need to check. If slot is smaller than 0, return false immediately. Otherwise, return slot equal to 0. Alright, we need to put this one as well. It's not just counting. I was very wrong. This one's false. But I return true because if we just count, it works. But it's not counting. Yeah, it's not counting. Alright. Let's try this one. Submit. Oh, that is not right either. What is the problem in this one? I said hold on. I said this is a null. Which means we don't have any slots to give, but then we have more things coming in. That's why this is a false. So is this, right? We do the first one, and then I think we should check this one. full, and say if slot is 0, then return false. Because we check if we have slot left to put. So in the swap this, when you check the slot first. Yeah, we check the slot first. No slot left. My God, it's like, yeah, we can check slot first, and if there is slot, we do something with slot. But if there's no slot left, but what happened to this one? For val in this, oh, because slot is 1. Initial slot is 1. Try this one. Yep, this one's correct. And this just don't even look at the time. Yeah, this is the one. Nice. It took me a few tries. Ah, yes. Yes. There we go. Alrighty, that's it for today. Oh, okay. We actually, yep, I didn't do very well. We build a tree, it's just not explicitly build a tree. So this is much easier, simple stack. Let's take a look at the stack. We see, replace it with this. If we get just 1 in the end, return true, else false. No, honestly, I think if you do this, I think this one might not be faster. I mean, this is always easier for me to understand. You know what? I mean, there is a value in doing it because this, we won't run into Stack Overflow, right? All right, so we split it, and then we add h1 if stack is larger than 2, and stack, the last 2 is this, and this is not this, then we pop, which means we hit the leaf. What does pop -3 and pop -2 mean? And pop that one. So we append the first one, right? And then -1, -2, both are this. And -3 is not. So we pop. But we keep the new one. Okay, let me think. So we have the tree coming in. So it comes in this, and now we have the left, right? And then we go to the right. And then when we go to the right, we say, okay, we have this, Then we'll replace it with this. Oh yes, because you're popping a leaf, right? When you pop this leaf, then its parent, it's as if the parent has a left node, whichever node it is, the parent have that leaf node as a none. That's yes. If we get just 1 at the end, so we just keep popping, and then we will pop this, replace, yeah, that's true, that was false. Nice, very good. I'll still go with this, but I see what this one is doing. replace with, that's the trick. This is the trick. This is the trick. All right. Anyway, that will be for today. I'll see you guys tomorrow. Adios.